Hi, I'm Luke, and welcome to our paper, Finding an Unsupervised Image Segmenter in Each of Your Deep Generative Models. This is work done with Christian Rupprecht, Erolena, and Andrea Vidaldi in the VGG group at Oxford University. So I'll begin with the presentation with motivation for our method and some related work. I'll then discuss our method and show some visual examples. Finally, we'll conclude with the discussion of potential future work. So we begin with the observation that although the field of computer vision has made tremendous progress on image generation with networks such as BigGAN and StyleGAN, there's been relatively little work using these models for downstream tasks. This paper takes a step in this direction by tackling the task of image segmentation by extracting information already contained in pre-trained generative models. Intuitively, our idea is that if a generative model is able to generate an image of, say, a bird, then it should also be able to identify birds and segment them out from their backgrounds. We're going to use this intuition to tackle the task of unsupervised foreground-background segmentation on a wide range of image domains without training any new GANs or inversion networks. Our method builds off of work from the field of generative model interpretation, which has seen rapid progress over the past 2 years. Prior work in this area has found that the latent spaces of GANs contain human interpretable directions, and there have been numerous methods proposed for extracting these directions without supervision. However, most prior work tries to identify these directions without the intention of using them for downstream tasks, apart from image editing. One exception, which we're building off in this work, found that one of the many directions in the BigGAN latent space corresponds to changes in foreground and background lighting. Our method also differs from most work in unsupervised image segmentation, which uses layer-wise generative models. These models are attractive because they produce segmentations naturally, but they have numerous drawbacks because they involve training new GANs, which is difficult and very compute intensive. Our method aims to find a segmentation direction within an existing deep generative model. Our method consists of 2 steps. The first step involves finding a latent direction V in the latent space of a pre-trained generator that separates the foreground from the background. We do this by optimizing for a direction which increases the contrast in the image while keeping the image edges the same. And we measure the image edges with a simple Sobel filter. Through this procedure, we find 2 directions, one which turns the foreground of the image dark and the background light, and another which turns the foreground light and the background dark. Here you can see some examples of this method, where moving in the negative direction makes the foreground objects darker, and moving in the positive direction makes the foreground objects lighter. Given these directions, we can construct foreground-background segmentation masks by simply measuring where the light-shifted images are lighter than the dark-shifted images. The second step of our method takes these directions and generates a large synthetic data set of masks and images, and then trains a standard segmentation model on this data. This step is essential because the previous step only produced segmentations for generated images, not real images. And here we show some final examples of our segmentations. So quantitatively, our method outperforms prior methods on 5 benchmarks, despite only being trained on synthetic data. More importantly, our method is agnostic to the choice of the underlying generator. It works well for a wide range of different GANs, with better GANs producing better segmentation results. Here, we can see the clear correlation between GAN performance and segmentation performance, which suggests that our method should also naturally improve as better GANs become available in the upcoming years. Future work could include extending these results to instance segmentation, new tasks, and to video. Our code is publicly available on GitHub. Thank you. I hope to see you at our virtual poster presentation.